Welcome. So I go to full screen mode in a moment. In the next 50 minutes or so, I want to take you through something which I have started working on about a year and a half ago together with Vincenzo Bonifaci, who is now a professor in Rome, and Girish Varma, who is a PhD student at the Tata Institute in Bombay. The original paper appeared in a computer science conference, but the full paper is going to appear in a journal on theoretical biology. If you want to have the paper, it's available on my homepage, and you can also find the slides of the talk on my homepage. So it all started for me when I watched TV. So this was about 18 months ago. I watched one of these science magazines on TV, and they reported about an experiment which 2 Japanese and 1 Hungarian biologist had performed about 10 years ago. And I'm going to show you the video of the experiment in a moment, but I want to explain to you first what you're going to see. So they built a maze, as you can see here on the left, out of cardboard. Now I should back up. So they experimented with a slime mold called Physarum. This slime mold can form fairly large cells, the size of a hand. This cell has many nuclei, and you can treat it absolutely cruelly, as you will see in the video. Namely, you can cut this cell into pieces, and if you put the pieces next to each other, then they will unite again. So what they did is they formed this maze out of cardboard. They made sure that the slime only can live on the maze. So they put this agar stuff on the maze, and they put some poison between the edges of the maze so that the slime cannot grow off the maze. And then they provided food at 2 places, shown in yellow here. Oh no, back up again. They covered the maze uniformly with the slime mold by taking little pieces and putting them on the maze. The maze would connect. So at the beginning of the experiment, there was a uniform cover of the maze by the slime. Then they provided food at these 2 places, and the slime mold would forage on this food, would move the food through its body in waves. And then, after half a day, the slime would have retracted from all the dead ends of the maze, and only the shortest path between the 2 food sources would remain. They report in the paper that they carried out this experiment with 10 different mazes, and in each case, the slime found the shortest path. So I saw this, and I thought, I mean, shortest path, this is my area. Yeah? And how come that the slime, it doesn't even have a brain, it has nothing. Yeah? How can it find the shortest path? And I would have forgotten about it by the next morning, most probably, but I opened my daily newspaper the next morning, and on their science page, they report about the same experiment. So it was reinforced the next morning. They also gave references in my daily newspaper. So I went to the Süddeutsche. So I went to the university, and the first thing I did is I retrieved these papers and I started reading them. They read about the experiment, but there were also some later on theoretical papers on the subject. And over lunch, I told some of my colleagues about it, that I would really like to understand this. How can this work? And yeah, this is how it started for me. And now I spend about 1/4 of my time on this. Before I continue, let me show you the video. So this is this Japanese professor, Nagagaki. The yellow stuff is the slime mold. Does not play, does it? I pressed some button. Oh. Let me restart it, maybe. Okay, so here he puts the slime on the maze in these pieces. You see the maze has about the size of a hand. You can see that you can treat the slime very cruelly. Yeah. Maybe I turn off her, so I hear also the... so now you see the pieces of slime on the maze. The pieces unite, and they form a single cell. Now next comes, yeah, you see the maze is uniformly covered by the slime. By the way, the slime is everywhere. Yeah, you can go into the wood and you find it. Now comes the food. It's oatmeal. The slime loves oatmeal, apparently. I promise you, it's going to be a serious talk. Yeah? Okay, now you're going to see how the food is transported through the body of the slime. The slime really loves this oatmeal. Yeah? You see it goes through the body in waves from both ends. Now it already starts to retreat from the dead ends. Yeah, here. We're going to see this in more detail in a little while. Also on the edges of the maze, it straightens out to form, yeah, here you see how it retreats from a dead end. And how it straightens out on the edges of the maze. And after about half a day, only the shortest path between the two food sources remains. Yeah? Amazing, isn't it? Okay, that's what I thought. It's amazing. Where is my talk now? Disappeared somewhere down here. Hope it doesn't complain if I have it twice. Oh gosh. No, I respelled it again. Okay, now we go, and now we can go to full screen mode. Where's my cursor? Where does it say full screen mode? Oh, up here, up here, up here. Okay, now we go. Okay, so there is something called the Ig Nobel Prize for inventions that make you laugh first and then make you think. This is exactly what happened to me. Yeah? It made me laugh first and then it made me think. Okay, now, fortunately for me, biologists started to develop over the years a theoretical model for the dynamics of the slime mold. I will describe this model to you. I will not argue that it models the slime mold, but these biologists do extensively in their paper that this is an adequate description of the dynamical behavior of the slime. So they say this slime is, you can model it as a network of tubes. Through these tubes you have liquids, food flowing, and tubes through which a lot, and this liquids and food flows through there through potential difference, concentration differences. Tubes through which there is a lot of flow will grow. Tubes through which there is little flow will shrink. Yeah? So for every sort of diameter of tube, there is a natural amount of flow through this tube, also determined by the potential differences. And if the flow is larger than sort of the natural flow, the diameter will grow. if the flow is smaller, then the diameter will shrink. Then they write down the equations for this. These are going to be a system of differential equations. And if you stare at the system of differential equations, you will see it's, and they observe this, that's exactly the same equations as for an electrical flow with time-varying resistors. And since we are all used more to electrical flows than flows of liquids, I will now switch to the language of electrical flows. And this appeared in the Journal of Theoretical Biology in 2007, this modeling. So they say, and the entire model is on this one slide. They say we have an undirected graph. Yeah, so the slime is modeled as this graph. Each edge in this graph has a length and a diameter, yeah, so a width. This length is fixed, it's given by the geometry of the maze, but the diameter, the width, is a function of time. Yeah? Now what we're going to do is, we're going to send 1 unit of current, and I will always say flow, 1 unit of current, from the source to the sink. So the source and the sink are the two food sources. Yeah? And the resistance of edge E is given as length divided by diameter. Yeah? So the resistance grows with the length of an edge, and it's inversely proportional to the diameter of the edge. Yeah? The wider the width, the smaller the resistance. And of course, the resistance is also a function of time, because the diameters are going to be a function of time. Now, in an electrical network, if the edges have resistances, if you force 1 unit of current from the source to the sink, there will be electrical flows in this network, and they are uniquely determined by the resistances and the geometry of the network. Yeah? By Kirchhoff's law and Ohm's law. Yeah? At least that's how the laws are called in Germany. I don't know, maybe in France they're called differently. So let me denote by Q sub E the resulting flow across E at time t. Yeah? And then they said the dynamics is very simple. You look at the difference between the flow and the diameter. You take the absolute value of the flow, because it doesn't matter whether the flow, if you have an edge here, whether it flows in this direction or in this direction. If the flow is larger than the diameter will grow. So the derivative of the diameter with respect to time is given by this difference. So if the flow is larger than the diameter will go up. If the flow is smaller than the diameter goes down. Now in this area, it's customary to denote the derivative with respect to time just by a dot. Yeah? Now, if the diameters change, the resistances change, the currents change, therefore the diameters change, and so on. Yeah? Now, it looks like here, as we have one independent equation for each edge. But that's not so, because the flows in a network depend on all the resistances. Yeah? So these equations for the individual edges are coupled. Yeah? Okay, so this is the dynamics. Now, when I think I do this also here, just to give you a short reminder of differential equations. What is a differential equation? Usually we think of equations in talking about numbers, x squared plus x equal to 5, and the solution is a number. A differential equation is an equation for a function. So the unknown is a function. And you put down an equation involving the function, its derivative, maybe its second derivative, and so on. Yeah? So sort of the simplest differential equation is this one. You're looking for a function whose derivative with respect to time is equal to minus a times the function itself. And then this is a function which solves, which makes this equality true. Yeah? Namely, if you say d of t is d of 0 times e to the minus at, you take the derivative of this, the minus a comes in front, and so the derivative of this function is minus a times the function itself. Yeah? So differential equation is an equation which talks about the function and the derivative, for example. And from now on, I will drop the t. Yeah? So all my quantities depend on time, but I will drop the dependence on t to make the notation simpler. Okay, so just to get a feeling for this, is let's talk at the simplest system. Yeah? So we just have a source and a sink, and we have two edges, and each has a length, and let's say the first edge is shorter than the second. That's not the way I have drawn it, but let's assume the first edge is shorter than the second, and they have some initial diameters. Now clearly, when we send 1 unit of current from here to here, the flow through the first edge plus the flow through the second edge will be 1 always. And therefore, if you look at the combined, the sum of the diameter of the two edges, yeah, d1 plus d2, and you take their derivative with respect to time, it's q1 plus q2 minus d1 plus d2. q1 plus q2 is 1, so it's 1 minus d1 plus d2, and therefore, as on the previous slide, we can conclude that d1 plus d2 converges to 1. Yeah? So the sum of the diameters converges to 1. And next I want to convince you that the first diameter converges to 1 of the shorter edge, and the diameter of the other edge converges to 0. Why is this the case? So assume both diameters are equal. Both are equal to 1/2, because their sum is 1. Well then, because the first edge is shorter, the resistance of the first link is smaller than the resistance of the second edge. Therefore, the flow through the first edge will be larger than the flow through the second, because they both work under the same potential difference. Therefore, because the sum is equal to 1, the flow on the first edge will be larger than 1/2, the flow on the second edge will be less than 1/2. Therefore, the first diameter grows, the second diameter shrinks, and this will continue like this until the first diameter in the limit is 1, the second diameter is equal to 0. Yeah? So this is what is going to happen. Okay, so much for this very simple system. We go forward. Yeah, now let's become more adventurous. In order to learn about such a system, one does computer simulations. Yeah? So let's recall that electrical flows are determined by potential differences. So in an electrical network, each vertex has a voltage, and the currents are determined by the voltage differences. So let me call the potential at vertex u p sub u. Then the flow across an edge is just the potential difference times the conductance, so the inverse of the resistance, and so this is times the diameter divided by the length. So this is the flow on edge uv from u to v. And we have flow conservation in all the vertices. So if you take any vertex u and you sum over all the incident edges, then the flow is 0. Yeah, so this sum must be 0. Except for the source, where it's +1, and the sink, where it's -1. Yeah, because we inject 1 unit of current at the source, we take out 1 unit of current at the sink. So these are the equations, and these equations talk only about potential differences. So you can fix one of the potentials to an arbitrary value, say to 0. You fix the potential of the sink to 0. Then these equations determine the potentials uniquely. And you can compute them by just solving a linear system. And if once you have determined the potentials, you also know the currents. Yeah? And so it's completely clear what you do in a simulation. You start with some initial configuration, some initial diameters. You compute the potentials. You go into an infinite loop. You work in discrete time steps. So you have diameters, and you make a small step. You compute the flows, as I described on the previous slide. And you do a small step in the direction of the derivative. Yeah? So you take the absolute value of the flow minus the current diameter. You take epsilon, the small number, let's say 1.01. You do a small step in the derivative. You recompute the potentials, and so on. And I mentioned that Intero, in their paper, introduced this theoretical model, and they also report about simulations. They say we ran simulations on 50 to 100 small graphs, and they report that in all the simulations, for the edges on the shortest path, the diameter converges to 1. For the edges not on the shortest path, the diameter converges to 0. So we re-implemented the simulator. I think we did it, I guess, somewhat more efficiently because we could also simulate really large networks with 50,000 vertices, 100,000 edges, and it always converges to the shortest path. So we ran some 10,000 examples, and it always converged to the shortest path. Well, if you run 10,000 examples and it always converges to the shortest path, then, at least if you're trained as a mathematician, you say, there's a theorem here. Yeah? Maybe if you're trained differently, you say, now I have understood it. Yeah? But this is not the way I'm trained. The way I'm trained is, okay, there is something to prove here. Yeah? That it always happens. And what I want to do in the next 20-25 minutes, I will not give you details of the proof, but I will more emphasize how we approached the problem, yeah? How we formed the conjectures which we finally proved. So what we did is we used the combination of, before I say how we did it, so what are the questions that we ask? Does it always converge for all initial conditions? Yeah, right. We had 10,000 examples, but does it always converge? How fast does it converge? Can we say something about the convergence process of how fast the edges go to 0 or how fast the edges go to 1? Can we only do shortest paths, or can the slime do more complicated things? In experiments, in lab experiments, in wet lab experiments, it seems to be able to do more complicated things. And I come back to that at the end of the talk. Can we derive distributed algorithms from this? Because the computer simulation is completely distributed. You compute the flows. For that, you only need to know the potentials of the endpoints. Then you need to update the diameters. Then you need to update the potentials, but that's also a local computation because the potential of a vertex depends only on the potentials of the neighbors. And so you can do an iterative process also for recomputing the potentials. And this iterative process a vertex only has to talk to its neighbors. Yeah? So it's a very local distributed process, and maybe this gives efficient distributed algorithms for shortest paths. We don't have good parallel or distributed algorithms for shortest paths. So maybe this is also an inspiration for distributed algorithms. Yeah, so we actually proved this always converges against the shortest path. Converges in the sense that for the edges on the shortest path, the diameter goes to 1. For the other edges, the diameter goes to 0. Miyagi and Onishi proved this previously, but only for planar graphs. And we proved it in full generality. Okay, so how did we do it? So we first looked at very simple systems. This two vertices just connected by a number of edges. because this system is simple enough so that you can treat it analytically. You can actually write down the solution to the system of differential equations. Then we did computer simulations of larger systems to gain intuition, to test conjectures which we formed by generalizing from the simple system, basically to kill conjectures, yeah? Because we had many conjectures by looking at the simple systems, and most of these conjectures most of the observations which we made about the simple system did not generalize to the general systems. Some of them seemed to generalize, so we did more extensive simulations on them. At the end, only one conjecture survived, which we then set out to prove. And luckily enough, we're able to prove it. We're able to prove. So, for a very simple system, I mean, not quite as simple as before. Now we not have just 2 edges, we have k edges. And let's say they are increasing length. So this one is the shortest, the next one is the next longest, and so on. And the case edge is the longest. You can solve the system of differential equations analytically. It's not too hard. And one sees that, yes, the diameter of the first edge goes to 1, all the other diameters go to 0. The potential difference between the source and the sink converges to the length of the shortest edge. But, and this came to a surprise to me, even there the convergence process is not completely trivial. Because what happens is, so the diameter of the first edge always grows. The diameter of the longest edge always shrinks. For the ones in between, it is at the beginning, only the longest edge shrinks and all the others actually grow. Then from some point on, the second longest starts to shrink also, and the k-2 longest still grow. And in this way, as time progresses, more and more edges start to shrink, and fewer start to grow. So, yeah, we understood this very simple system. And then, yeah, if you want to prove convergence, you sort of ask yourself, yeah, in mathematical terms, you ask yourself, what is a Lyapunov function? So a function which goes down over time. I guess in biological terms, you ask yourself, what does this dynamics optimize? Yeah, I mean, it's there to make the slime survive. Yeah, so there must be some global goal which the dynamics optimize. Yeah, and the first thing we thought is energy. Yeah, this slime tries to minimize energy as it evolves. Maybe this was not so, I mean, it was a naive idea probably. If you have enough food, there is no point really in optimizing energy. Yeah? And there was enough food in these examples. So the first thing we thought is we just look at the energy of the flow, which is you sum over all edges, the current times the potential difference. So I use always delta sub E for the potential difference on an edge. So this would be the energy of the electrical flow. And you hope that this decreases over time. But that's not even true for the parallel links. Then what we did is we sort of wrote down natural functions which one could think this thing optimizes. So what are natural candidates? Well, for example, this here. This you can think of, in a certain sense, the cost of the flow. Namely, for every link, you look at the flow across the edge times the length of the link. Yeah? So this is the total, if you think of, you have to transport goods from the source to the sink. If you transport Qi units over a link of length Li, it's natural to assume that this has a cost of qi times li, and you sum over all links. So this is the cost of the flow. And for the case of parallel links, it is, in fact, it decreases over time. So the network becomes more and more efficient. This is also a natural quantity to look at, this here. What is this? You sum over all links the diameter of the link times the length of the link. The diameter of the link times the length of the link you can sort of interpret as the hardware cost of the link. Yeah? It has a length, it has a diameter, so this is how large the amount of stuff that you need to build the link. Now, this is what we thought would go down, but if you go through the math, you notice, no, you have to normalize this by the total diameter. But if you look at this quantity, it goes down over time. And we found a few more. So we found about 10 quantities which go down over time for the case of parallel links. And we found them by guessing. Yeah? We said this looks like a reasonable function, and then we tried to verify it analytically. Yeah? And the functions we looked at are all those functions which sort of have a natural interpretation. Yeah? Is cost of the flow, hardware cost, and a few more. And then, I mean, yeah, these are parallel links. There's a natural way of generalizing all these functions to general graphs. You do not sum over the links, you sum over all the edges. Yeah? So you sum over all the edges, and none of the generalizations worked. Yeah? So we ran simulations, and none of these functions went down all the time. Say, one was close. This one was very close. Yeah, this one was very close. I think we ran simulations on 10,000 graphs, each one for 100,000 steps each. And this function would go down in all but 15 steps. Yeah, so out of these 10,000 times 1 million, it went down in all but 15 steps. Now, what does it mean in a computer simulation to go down? Yeah, because there are round-off errors, and yeah, the way you implement going down is you say it doesn't go up too much. Yeah, and once we looked more closely, it failed more often. Yeah, so this function was also out. So yes. Oh, yeah, the potentials at the source and the sink. Oh, I'm sorry here, yeah. P source minus P sink.
And how do they move again?
Pardon me?
PS and PT, what's the evolution of that?
They are fixed.
Oh, PS is fixed.
I'm sorry, just PT is not time here. This should be source. I called this, I think, S0, and this should be sink, S1.
If it's fixed, why do you bother putting it? I don't understand.
No, the potential difference is not fixed. We're sending one unit of current from the source to the sink. So the potential difference can change over time. Okay? Okay, so at this point we got stuck. We had done the analytical investigation of the very simple networks. We had tried to generalize. We did the computer simulations, and none of our conjectured potential functions, Lyapunov functions, worked. And yeah, then I guess there was a strike of luck. So we had this function, and just replacing the i's by e, so summing over all edges didn't work. And then one of us observed that this quantity at the bottom can also be interpreted differently. Namely, you ask yourself, so here is the simple network. You have the source, the sink, the k parallel links. If you ask yourself how much diameter you have, so you want to ask yourself, I want to separate the source from the sink by cutting edges. And of course, if I want to separate the source from the sink, in this very simple network, I have to cut all the edges. So this is how much diameter I have to cut. But in a general network, in a general graph, you don't have to cut all the edges if you want to separate the source from the sink. Yeah? You have to cut some edges. And the total diameter of edges cut will be different. It will depend on which set of edges you cut. Yeah? So we said another way of generalizing this is you replace this by the minimum total diameter of a source sink cut. Yeah? So you ask yourself, how much diameter do I have to cut in order to separate the source from the sink? And you take the minimum of all ways of separating the source from the sink. Yeah? So we had another generalization of this. We had another candidate. And this candidate worked. So we used this in computer experiments. We ran extensive experiments and it always went down. So then we set out to prove this, that it always went down. Well, we started out proving it. It's not true that it always goes down when you do the proof. Because there is a degeneracy. If you start out with a network where which is already in, so you take, how should I say this? Well, you have to, let me not argue. You have to add in a fudge factor, which is this factor here, which is you sum over all the edges incident to the source, you subtract 1, and you take the square of this. So this is the simplest cut, which just separates S in the obvious way from separating from the remainder of the network by cutting all the edges incident to S. And you look at the diameter of this cut minus 1 and the square. This you need to add in to make the mathematics work. So we first proved that this function always decreases. It's not, yeah, let me say a few words about the proof. So you compute the derivative of this function, and you find out, after massaging the expressions a little bit, it requires combinatorics. For example, it requires the min-cut max flow theorem, namely that in a graph, the minimum cut of separating two vertices is also the maximum amount of flow you can send from one vertex to the other. It requires that the electrical flow is, with respect to energy, the most efficient flow. But if you put all of this in, you find out that the derivative of this can be upper bounded by this. Yeah, so it's a sum of, you sum over all edges, diameter minus flow squared. So the derivative is always negative. Yeah? So the derivative is always negative. Now, this potential function, because the derivative is always negative, this function decreases. Just by the way it looks, this function is never negative. So this implies that the derivative must converge to 0. Now the derivative was upper bounded by this, and this must mean for all edges, the difference between the diameter and the flow must go to 0. Now the difference between the diameter and the flow, if this goes to 0, this can only be in either of two ways. Either both quantities go to 0, or the ratio of the two quantities goes to 1. Yeah? And this means for the edges on the shortest path, yeah. So this also means that for these edges where the flow is a substantial amount, you must have, because the flow is given by the diameter times the potential difference divided by the length, that for those edges the potential difference is approximately the length. And from this one can conclude that the potential difference between source and sink converges to the length of some source sink path, And if one works a little bit harder, then one can also show it converges to the length of the shortest path, and then this implies that the diameters go to 1 and the on the shortest path, and the others go to 0. The theorem assumes that the shortest path from the source to the sink is unique. If this is not unique, it's more complicated. Then you converge to a flow. You look at the network of all the shortest paths, and in this network it converges to a flow of value 1 from the source of the sink, and which flow it is depends on the initial conditions. Yeah, so it converges to a flow of value 1. Yeah. Now I turn to the open problems, where I have only partial answers. So, how fast is convergence? So what we only know is, so the flow through an edge can change directions. We have examples where in the simulations the direction of the flow changes 7 times. Yeah, so it can change. Yeah, it flows from here to here, then from here to here, and so on. But it seems in the simulations that from some point on, the directions stay stable. I have no proof of this. Yeah, it's just that in the computer simulations, I never observed more than 7 changes. Yeah, but maybe if graphs are larger, I observe more changes. Yeah, maybe 7 is 10th root of the size of the network. I don't know. Yeah, so it. But if a network stabilizes from the point on where the directions of the flows are fixed, then the convergence is exponential. So all the edges that converge to 0 go down like e to the minus something to the t. Yeah? So once flow directions are stable, convergence speed is good. But whether this stage is reached and how long it takes to reach it, I don't know.
So what happens if you have 2 paths that are, there's the shortest path and there's one that's very, very near the shortest path, that's slightly higher?
This exponent, this e to the minus, the rate, depends on the length difference between the shortest path and the other path. Yeah, so if there are 2 paths which are very close, it takes longer to converge. Yeah, do networks stabilize? If so, after what time? Here is a graph which you might remember from your physics class. In the physics class, one uses it to measure resistances. A very simple network. There is the source, the sink. It should be again S1. There are these 5 edges. It's clear that on these outer edges, the flow is always downwards. But on this middle edge, it can go either from left to right or from right to left. And here we have examples where it changes. Yeah, so this is the simplest network where it's not clear whether it stabilizes. Yeah, because the flow on this edge can be go from left to right or from right to left. But for this very simple network, we can prove that it stabilizes. But it takes 3 pages of arguments, which cannot be. I mean, we don't understand it, yeah, sufficiently enough. But for this very simple network, we can prove convergence. Let me not go through the math. So we can also prove that the slime mold can solve a more general problem, not just shortest path. It can solve transportation problems. So there, you have several sources and several sinks, and the total amount injected into the network is the same as the amount that is taken out, and you're searching for a most effective way of transporting goods from the source to the sink. It also solves this problem. open problems, or problems I'm thinking about. So I assumed that all edges react in the same way. Yeah, there was this equation, but there are very interesting experiments that the biologists have done. So this slime doesn't like light. It prefers to grow in the dark. So if you do the following experiment, you cover a rectangular plate with slime, you provide food at the two ends, and then you put half of the plate under light. Then it does not form a straight line, as it would in the dark, but it forms a line with a kink, yeah? So that the part of the path which is under light is shorter. Yeah, like Snell's law it looks like these paths that one sees in optics. Yeah, when light goes through solids where the speed of light is different. Yeah, so so mathematically, you would introduce a constant here on the right-hand side of the equation, and which depends on the edge. Yeah, can you prove convergence for this? There is a paper by Ito and Johansson and also by Nagagaki and Tero where they removed the absolute value signs on the right-hand side. Not because they say this is biologically reasonable, because I guess because they were frustrated about not being able to prove convergence with the absolute value signs. So they removed them and hoped that the simpler system they can study. And they proved convergence without the absolute value sign about at the same time as we proved convergence with the absolute value sign. The convergence proofs are the original convergence proofs, theirs and ours, are quite complicated. They're 30 pages each. But since then, Vincenzo found a simpler convergence proof for our model, and I and my PhD student, Michael Dierenberger, we found a simpler convergence proof for this model without the absolute value signs. I don't know how fast convergence is. I described, or I know, the Miyagi and Onishi, the two theoretical biologists, they described the dynamics as a system of differential equations. Can you describe it as a particle system? Now, it is known that electrical networks can be understood as random walks. Yeah, so if you do the following, you say you have this graph where each edge has a conductance, and you inject particles at the source, and then this particle performs a random walk. And whenever it sits in a vertex, it looks at all the outgoing edges, and it takes an edge proportional to the conductance, with probability proportional to the conductance. Then this random walk simulates or is equivalent to the electrical network, in the following sense that for example, the voltage in a vertex is the same as the probability that when you start in a vertex, that you reach the source before you reach the sink. This can be interpreted as voltages. And transition, the time you go over an edge, that can be interpreted as currents. So this gives rise to a particle interpretation of the flows, and this needs to be explored. Because I think particles give more intuition. They are harder to manage mathematically. But, and I come back why I think they give more intuition. So this slime can apparently do more than just show this path. So here is a very nice experiment, which Again, the two Japanese did. So they formed a model of the greater Tokyo region. Yeah? So they made sure that the slime cannot grow into the ocean, and it cannot grow up Mount Fuji. And they provided food not only at a single place, but they provided food at many places. And they provided food according to population density. Yeah, in the greater Tokyo region. So there was lots of food in the center of Tokyo. There was less food in the suburbs. Yeah? And then this slime forms a network. This is shown here on the left. Yeah? So it connects the food sources, which are shown in yellow, by tubes. And yeah, and then the paper ends with just two pictures. It overlays the network formed by the slime by the network, by the railroad network around Tokyo. And the authors say, don't they look surprisingly similar? Yeah, so I mean, I guess what they want to say is that this slime, the network formed by the slime is a good network. Yeah, it has short connection costs, it has sometimes multiple connections, maybe to increase reliability or to, yeah. Now, this is very hard to understand if you think about, I'm trying to understand this in the moment, and how do I approach it? So, when you talk about an electrical, so this is really, mathematically, I think it's a multi-commodity flow problem. Yeah, you have people that want to travel from, some people want to travel from here to here, some people want to travel from here to here, other people want to travel from here to here, yeah? And of course, it's important that a person who wants to travel from here to here goes into the network here and comes out here, yeah? So just the transportation problem that I talked about will not work. Because there you only say you inject people at places and you take out people at other places, but you don't care where they come out. Yeah? But now you insist that somebody who goes in here comes out here. Now this is very difficult to model. I mean, I found no way to model this on this level of, because you now would want to talk about sort of a green electrical current, this is the one going from here to here. A blue electrical current, that's the one that's going from here to here. Yeah, sort of you want to distinguish the different flows. Yeah, but when you talk about particles, that's quite simple. Yeah, there when you think of current as particles, you can talk about green particles that go in here and must come out here, and blue particles that go in here and come out here. There's no problem sort of intellectually, yeah? And it's also clear how they should reinforce the network. For example, you would say if you have blue particles and they go across an edge in opposite direction, you don't want to reinforce this edge. They should cancel out each other, yeah, because they're both looking for a path from the source to the sink, and there's no point in doing this. This is exactly when you talk about currents, yeah. Then currents, things that go in opposite direction, cancel out. However, different if you have particles going from here to here and particles going from here to here, if they go across an edge in opposite direction, they should reinforce each other. Yeah? There they should not cancel out, they should sort of help each other. There is more, yeah? So the particle view allows you to distinguish different currents of different types. Sometimes they should cancel out as real currents. Sometimes they should add. Yeah. So the particle view tells you where you should do a minus sign and where you should do a plus sign. And so I have a conjecture now, actually only since this morning from the train, of what the slime optimizes in the network. And I have to test this out now in computer simulations, and then if it survives, if the conjecture survives the computer simulations, then start out proving it. I come to an end here. If there are any questions.